to heat that up, what will happen to the volume? It'll expand, it'll increase. If I put it into a sealed, immovable container, my gas, and I heat it up, what will happen to pressure?
Increase.
It'll increase, because all the little molecules are doing what? They're moving more and more with increased heat, so that means increased pressure and expansion. Very good. So, there's page number that I just mentioned. This first part of the lecture, we're going to talk about fluid mechanics. Another fellow, two other fellows, Pascal's law and Bernoulli's principle. And then we'll talk about sound. Then we'll do some lab. And then we'll have a second part of lecture. So, fluid, the definition somewhat, various definitions, but one, the molecules are able to flow past one another without destroying the material. So if this desk, I tried to make the molecules flow, I'd have to take a sledgehammer to it, that would destroy the material to make those molecules flow. But by nice lemon water, I can slosh that around, make it flow, and it's still lemon water in there. Gases, we learned yesterday, are very compressible. Liquids are considered not compressible. So, would gases and liquids both be considered a fluid?
Yes.
Yes, because they both, molecules can flow past each other without destroying the material. So, a fluid is a form of material that will conform to the shape of its container, but it's considered, under normal circumstances, not compressible. So, I can show that to you. I've got a syringe here, and if I fill it up with 8 cubic centimeters of air, and I put my thumb over the end, I can, and I have it sealed pretty good, I can squish that down to about 1 cubic centimeter. And then, you hear the psst, because there was a lot of pressure in there. I went from where it was happy, and there's not building up pressure, but I am decreasing the volume in an enclosed container, so therefore pressure is doing what? Increasing, which is why when I do that, it goes psst, and releases very quickly. Now, if I take 8 cc's, try to get this all water in there, and it is water, nothing, no other fluid. And I put my thumb over the end and seal it off, and I cannot make it budge. Try hard as it might, and if I let my thumb go, we'd have a nice stream of water. So, very quick, simple way to show fluids under normal circumstances are not compressible, which you need to know this in aviation, because if really bad situation, you get water ingestion in your cylinder, or more commonly, you get a buildup of oil in there on a big radial engine, your cylinder that's at the bottom can get oil drained into it, which is called hydraulic lock. And if you don't clear that out before you start your engine, you fire it up, and this poor, nice, straight connecting rod tries to shove that piston up the cylinder, but there's fluid in the way. Well, the piston does not go up. The rod spins because incompressibility of that fluid wins over the strength of the connecting rod. So that's a very bad day. And you have very sad pilots and very sad mechanics. Gases being compressed is very, very useful because for our fuel, we have a big old fuel tank out there. It has to contain the volume, the total volume of the fuel, liquid fuel. Our compressed gases, they can take a the buoyant force is greater than the object will float. So that's why how they design boats, to be able to float in water. And to find out what the buoyant force is, they take a pan and fill it up right to the spout with water or whatever fluid you're measuring. And then you take 10-pound weight or whatever, and it's 0.11 cubic inches. Place that in the water, and it will displace the same volume of water, and then you can weigh that, and that will tell you your buoyant force. It's not something you'll really have to calculate, but just to understand that buoyant force equals the volume of the object, so volume is the same, times the density of the fluid displaced, which they can test that way. Where this comes in, did you see that?
That was amazing.
Thank you. Where this comes into play in aviation, depends where you go. If you will deal with airships, but they're filled with helium, and then that is held up by the buoyant force of the atmosphere in the air. What you might deal with, and shout out to Case, is float planes, and they have to design the float to support the weight of the aircraft, so the whole thing is more buoyant than water. So they have to be designed large enough to displace a weight in water equal to the airplane's weight. That's the first thing. But when you see a float plane, most of the float is actually above the water because regulations dictate that the floats, rather than just supporting the weight of the aircraft, they actually have to be 80% larger than the minimum needed to support the airplane. So that's why you want to make sure you're super, super safe out there floating around on the water. Pressure with fluids can be a little of a unique thought process. The pressure is the force exerted per unit area. So per square inch or centimeter or whatever unit you're using, and fluid pressure changes with height. It doesn't matter the shape. So all of these for we have 1 square inch, and it's the same height. This one, we're wider at the bottom, and this one we have a weird shape, but all of these are the same height. So for every square inch, we've got the same pressure. Kind of like, who trusts me? I think your hand was up first. So, lay your hand down on your butt. Would you rather I drop this like that, or like this?
Probably the other way.
That way? You're correct. And why?
Because the weight is displaced over a larger area.
Yes. And even though this is a solid, it's the same concept. The pressure changes with my height, so you're gonna feel more pain if I drop it this way, or especially if I drop it but
Oops.
more pain this way than that way. And so you know what damage you just avoided.
Oh, that's great. Sorry, Nick.
Ting. So, in a fluid, pressure changes with height, not shape. So, taking that pressure down here, will the pressure at the bottom be the same as the pressure halfway up? No. It'll be half about. Will the pressure halfway up in this one be the same as the pressure halfway up in this one? Yes, because they're still the same height, as long as we measure exactly halfway in both of those containers. Now, there's two terms, and you're going to learn a whole lot more about these two terms in instrument class: static pressure and ram pressure. And if you're a pilot, you might already be familiar with these terms. But static pressure is pressure based on column height, or you might have heard the term head pressure. So if we have a carburetor down at the bottom of the engine, where are we going to put our fuel tank so that we get the pressure that we need if we don't have a fuel pump, if we just have a gravity system?
Highest point.
The highest point. So that's one of the reasons they put the fuel tanks up in the wings. Especially, I mean, we'll talk about fuel pumps and everything, but if you don't want a pump on your engine or on your just your fuel system from your fuel tank to your carburetor, you got to make sure you have enough head pressure or enough height in your system so that you have enough pressure at your carburetor to get fuel flowing into that system. So that's just, they will measure that statically stationary without the fuel flowing, just to see what the fuel is from the bottom of the system to the top of the system. And then ram pressure is the fluid in motion. So we'll talk about ram air coming in the front of the engine cowl, and you want that moving air, the fluid of air, moving over your cylinders and cylinder fins to help dissipate that heat, carry that away. And we'll also talk about ram and static pressure in turbine class, because turbines take advantage of both of those. And then airspeed indication systems, we'll talk all about that with case. But just know static pressure is fluid not moving, just taking the pressure at the bottom of the system. Ram pressure is fluid in motion. Now we get to a fine fellow, Mr. Pascal. And he came up with a law that you need to know. I know it's an open book, but make sure you memorize this for written oral testing. So, Pascal, dropped my sanitizer on my notes. Very clean notes now. Mr. Pascal realized that pressure is transmitted through a fluid. So I can put pressure on this object and fill this cylinder with fluid, and I get pressure out the other end. So it's a very useful thing. And he was the one that realized pressure at the same height is the same, and that the pressure is transmitted equally in all directions. So if I'm putting in a force of 5 pounds, whatever pressure that equates to, I'm going to have same 10 psi here, 10 psi here. If I take it here, 10 psi, so it's equally distributed pressure in the entire system. And the pressure acts at right angles to any surface. So, very smart fellow came up with this formula that force will equal pressure times area. Area. There you go. So where the force is applied, that area divided by pressure. And if you're more visual like I am, rather than trying to memorize those, you can picture this triangle with force at the top, area and pressure below it. So force equals area times pressure, or area equals force divided by pressure, or pressure equals force divided by area. Yes.
I'm thinking through this, and I don't mean to be confusing or nitpicky. Would it be fair to say, in the picture on the left,
Yes.
that even though like 10 psi is like the pressure it is,
Yes.
would it be fair to say that at the very top, it would just be a little bit more than the pressure at the bottom? Like, not measurable, but would that be how it would work, or not really?
It should be exactly the same.
Even though it's like...
Are you thinking that if we
thinking-
turn a gravitational pull?
Right, well, because in other places, pressure, the lower you go, the more pressure you have. So, I'm just trying to merge the two together in my head. It wouldn't matter.
Right. It would be
It's a
very,
container.
yeah.
Would it
closed
be
container.
fair to say that, would that not?
I don't think so. I'd have to look into it, but
Because it's
It's an
sealed.
average.
right, sealed container system. You have a pump or something putting pressure on it.
Gravity still active when you measure.
Okay.
I'd have to
So
look.
pressure is trying to equalize.
Yeah,
So if you put more pressure into one side, it's gonna average with the other.
Yeah, it wouldn't affect anything. It'd be very negligible if it is.
Sure, I was just thinking of the physics. Thanks.
Yeah, no, that's a good thought. Yeah,
So Pascal, is he the one who came up with these formulas?
yes,
Okay.
yes. He did a whole bunch of
We know
studying,
who
scientific lab stuff, discovered this, and now it is a law because it always is this.
Passed by Congress?
Oh no, it's way better than that. Scientifical. So, in aviation, our force is going to be measured in pounds, pressure, psi, area, inches squared generally. Maybe you'll have centimeters, may have inches, but pretty much you'll have pounds per square inch. So pounds per square inch is how it'll be quantified. And just how those numbers would go, we have pressure, so we're grabbing that formula, equals force divided by area of our piston. So pressure equals phi divided by 1/2, which does equal 10 psi. Now, your turn. How many people need a scrap piece of paper? Yeah. Anyone else? If you happen to need some, feel free to grab. Alright. So, this is a prepware question. I'm working through these because they can be a little confusing, and I want to make sure as you're studying prepware that it does make sense to you. So, it says, if the fluid pressure is 800 psi in a 1/2 inch line supplying an actuating cylinder with a piston area of 10 square inches, the force exerted on the piston will be what? So, what in the world are we trying to find? Which of the formulas are we going to use?
F equals A times P.
Yes, we're trying to find force. So force will equal pressure times, so force equals pressure times area. And what is our pressure in this system? 800. 800 psi. And what straight, you're right. It is, piston area is 10 square inches. So this is the area we're concerned about. What should we do with that 1/2 inch supply line? Disregard it. Bury it. That's not important, whoops, to us. I'm getting out of control. So, that's just fluff information. So yes, the 10-inch piston area, and so therefore, our force will be what?
8,000.
Whoa. 8,000 pounds of force that we're giving out here to whatever this is actuating. Questions? Confusion? We'll do another one. And we'll see if I have redeemed this eraser. Oh my goodness!
Into oblivion.
So you know, if you ever feel like you're thrown into a trash can, you're redeemable.
You wash that off.
I did. That's all it. Whoa! Literally, I washed it, and we just need washed in the blood. All right, I'll stop reading now. Next question. If a double actuating cylinder, what do you think it means by double acting? Yeah,
There's fluid like on the back side of the piston.
right. There is fluid on both sides. So, yeah, that's all it means. And in case of hydraulics class, you'll learn all about the details of that. But if a double
Do we need the same spot?
a double actuating cylinder in a 3,000 psi system has a piston with a surface area of 3 square inches on the extension side. Now this can be confusing, but that means the side where the force is causing it to extend. So this is what, so the wording is confusing, but this means extension side because it's the force that's causing the extension stroke. And a rod with a cross section of 1 square inch, 1 square inch, is attached to the piston on the other side. Approximately how much force will the actuator be able to produce when retracting? Ugh, very confusing wording, which is why we're working through it. So, first of all, which formula are we using?
We're using the same one, trying to find force.
We are, because I said how much force. So at least we know we're starting with that. So force equals what? I didn't put the triangle up.
AP.
Pressure times area.
Do we get rid of the cross-section information? Do we need that?
We're going to talk about that.
Okay.
So force equals, what is my pressure in this system?
3,000 psi.
3,000 psi times the area. So which side do we have to calculate the area for? The one with the rod or not the rod?
The one
The one
with the rod.
with the rod. So it's talking about this side here where we are retracting or a return stroke. And what is the area of this whole piston?
3.
subtract it because what?
It's taking up space.
But it's just taking up space and there is no fluid pushing on this rod. It's attached to some mechanical something out yonder. So we had to subtract that part off. It doesn't have, taking up space, fluid can't be pushing on that part. So, yes.
I have a question. Did you say the force is perpendicular? What did you say? You said pressure acts at a 90 degrees
Oh, right.
to the surface?
Yes.
So,
Yes, so our pressure of 3,000, it's pushing here, it's pushing there, it's pushing here,
okay.
in a
but-
closed container.
That wouldn't affect any ever.
Right. Right. But if we take away the pressure on this side of the piston, then this pressure is going to move that piston with the force that we're going to calculate. So, oh yeah, we said subtract, so 3 minus 1 equals what? Woohoo! 2 inches squared. And 3,000 times 2 equals what? 6,000 pounds of force being exerted on that piston. Questions? Okay. Yes.
So if the piston's going the other way, there'd be no force.
Oh, wait, what, say what?
If the piston was going the other way, there'd be no force because that rod would be there.
Correct. Well, yes, there'd be more square inches, yes. It depends what our pressure is on that side. But, yes, same scenario. Actually, yeah. Yes, yep, because you have more surface area. Alright, so we have one more formula. Well, there'll be lots more formulas, but another one that relates to this. And you can find it in your book on page 5-30. And you might, so on page 5-29 is a force equals pressure times area. Make sure you mark that. You can come back to it on Monday when we have your final. And then this one you want to mark as well. So the formula is input piston area times the distance moved will equal output piston area times distance moved. And we can use this for very handy things like brake systems and hydraulic systems. So our output piston area then just like our other problems we worked, go back and make sure that 20 times 1/4 equals 5 times 1. End of shift. Questions on that one? And
That was quarter times 20.
correct.
And then after that equals output piston area, 5 inches.
Correct. Times.
Okay, times 5. Oh, wait.
So it would be the 5 times your unknown, which is the distance. So then you just multiply 1/4 times 20, divide by 5 to get distance by itself, and that'll equal.
Okay, I'll do it.
Yep. Yeah.
And whose wall is this?
I was saying yes to him.
Since liquids can't be compressed, are we assuming that this system is like 100% efficient?
Yeah, for these problems. Yep. Joe, was that you?
He had the same question. It's crazy.
Was it?
Are you serious? I don't know. What would you put?
Whose wall is this?
It is. Oh, actually, if you look at your book,
Still Pascal is.
it is still Pascal's law. Continuation. He was one busy dude.
Good job.
Like Dean says, these guys that lay awake in their bed at night dream up this and go prove it during the day, and then they get to retire Mackinac Island.
Well, you said one more formula, and then you didn't give a name. I was like, they all have names except for the last.
Right.
She came up with it.
This is the Christina
Whoa.
number. I couldn't do that. I can tell you how to use them. I don't know them. Alright, so we're going to take all that we learned. We're going to take Pascal's first law. Oh, I won't go back. Okay. And this formula, and we're going to put it all together. So, I highly recommend that you have a very nice sheet of paper, whether you want your own nice sheet of paper or you want a brand new nice sheet of paper. Everyone needs to write down what I'm going to write up here on the board, unless you think you're too good for that. Because a problem extremely similar to this is going to be in your lab as well as on your final. Now, all the numbers are going to be different. I switch up all the numbers. But you can use your work from this problem to help you know what formula and what process to use for your lab as well as your final. Your final's an open book. So, anybody need some paper? Alright, and as we go through it, if you're like, I'm running out of room, feel free to grab more paper. You can label this legal assistance for final exam. Whatever you like. This will be your very own personal paper. I don't need to see this. Okay. So, if you want, you can draw a little triangle if that helps you. Force, area, and pressure. Or you can make a little note of what page it is in the book, which is page 5-29. So you can turn to that page while you're taking your final. So it will ask you, it will give you some information. So our force for cylinder A, we're pushing down with 10 pounds. That piston moves 8 inches. force coming out of here, how far, what is the distance that it's traveling, and what is the work? Huh. Oh my. Alright, so what do you think we need to do first? I heard it somewhere. What would you do first for this problem?
Find the PSI.
Ooh, find the pressure. And put forces up here first. Why are you finding pressure?
To know the force of the other cylinder?
Yes, because you need the pressure to be able to find the force. Because the formula for force is what? It is pressure times area. So we need pressure to be able to find the first thing they're asking for. So pressure, what is the formula?
Force divided by area.
Thank you for answering what I was asking. So it's force divided by area. So pressure, and what is our force coming in over there? 10 pounds divided by, what is the area? 2. And then now, pressure equals, what is 10 divided by 2? Woohoo! 5. So we can have that now to come over to our force problem. So we've got pressure, which is 5 pounds. And which area are we going to use? Correct. We're looking at the force coming out of here, so it is 14 square inches. And 14 times, or 5 times 14 is what? 70 pounds. So we finally got the first piece of information they want. When you are doing your lab, when you're doing your final, make sure you are labeling units. Okay. Then they want distance. So what formula are we going to use for that?
Pascal's other law.
I like that. Pascal's other law. And what is the formula?
Input piston area times the distance of the input piston.
Input piston area times distance equals output piston area. I'm abbreviating. Whoops. Output area times distance moved. And where would you go in your book if it's testing? Oh no! Where do I find it? Page number 30. 5-30. So make sure you have that marked. So what is our input piston area? Yep. 2 square inches times, how far did that piston move? 8 inches. And what is our output piston area? And we need our distance moved. So then, 2 times 8 is what?
16.
Equals 14 times distance, divide by 14. 16 divided by 14 is
1 1/4.
point,
143.
yes, I got 0.143. So, we can put that up here, 1.14, and what units is with that? Inches. And then they want the work done. What formula do I need for work?
Force times distance. Work is force times distance.
It is force times distance, and that is back in the book from the other day.
Where'd you get the 8 from? The 2 by 8.
The distance.
Oh.
That it.
Yeah.
So, work equals, now, we want to know the work for cylinder B, Bravo, so what force are we using? 70? And what distance are we using? 1.14. And what does work equal?
80 inch pounds.
Yeah, so 79.8, or you can round it to 80 inch pounds. How would we double check that?
Divide by 1.4.
There's different ways you could go about it. But if input area times distance, so what? 2 times 8 here. Wait, I'm looking at the wrong one. So force times distance should equal oh yeah, I'm still back on the force times distance, yeah. There was a, yeah. Oh, yeah, all right, okay. Thoughts. So how would you check the work from cylinder A? You would do,
Divide by 10.
yep, force times distance. So you can go back and make sure you get 80. Now, we rounded that number, so it'll be slightly different, but should be very close to 80 for both. So yes, force times distance on cylinder A would be 10 times 8, 80, which equals 70 times 1.14.
So that force is on both cylinders together.
No. Cylinder B force is 70 pounds. Cylinder A force is 10 pounds. Because we have,
That's what's given.
small force over long distance, large force over very short distance. Which is why force times distance should equal force times distance. Yeah.
Is work always defined as the product? Like whatever we put in, this is how far we got, basically. It's not the work we're putting into it, it's always output.
Yes.
That's the work.
Yes, because
Okay.
I can push on this wall with all the force, but if the wall doesn't move, there has to be distance involved for work to happen. I'm going to hide this a second for my next little part, but then I'll show it again while you're working it out. So, where this comes in is brake system is one really good example of it, and you'll be working on brakes in landing gear class. So, you put in a small force over a long distance to get large force over a very short distance. So that's why you can just ease on the brakes and your whole aircraft stops, hopefully, if your fluid is correct in your system. All right, take, I'm going to give you until 20 to work on question 9 of lab
obviously, there's obviously emulsions. Anyway, this measures force, is that gonna be the PSI or the total?
The force, like here, this one's 50 pounds, this one's 40 pounds.
Something wrong. How much distance is this? He's only walking, just rough. Working professional. Force. That was my first one. That's before I started this. If I need to break it out, which is using the wrong numbers. It's like there is. Wait, what'd you get for yours? That's what. What'd you get for yours? Work each pound. Took the 10 times. That's what it is. Work equals force times distance. 300 pounds. How much distance? 5 inches. 5 inches. Sure, there's work in this. Yeah. So 300 times 5.
It's just added, so when you're pressurizing accelerator, if it's not pressurized, pressurize it, they're both supposed to just add it to it.
How much force is in the front? How much force is in the front? You already saw that. That was the information given from Robbins.
Now, the answer you're gonna assume is the same, but I'm not, that's actually how you check it.
You need somebody with a lot of hot hair, man for the job.
All right, we're missing some people, but it's time to get started again. So they'll just miss out on this amazing demonstration. I'm not gonna say what our next topic is yet, but you all know, Case, big strong dude. So, so he has a ping pong ball and a funnel. If he places the ping pong ball in the funnel, do you think he can blow that ping pong ball right out of the funnel? Somebody say, oh yeah. No problem. All right, go for it. Don't kill yourself. What? Okay, that's good. Breathe.
Hopefully they didn't have
like, now, how many believe we can turn the funnel upside down, put the ping pong ball in it, and the ping pong ball will not yield to gravity? We got one person who has faith. 2, 3, okay, come. Alright.
I mean, I only got so much air, people.
That's good. Thank you. somebody with greater lung capacity. Why do you think, what principle do you think was just demonstrated?
Bernoulli's.
Woohoo! Bernoulli. So, Mr. Bernoulli stated that if you take this device called a venturi, which is a tube that narrows and then widens again, and you pass a fluid through that tube or duct, when it converges, and a convergent duct means it is narrowing down, the velocity of that fluid is going to increase. And the pressure will decrease. After we get through the narrow portion and we have a divergent, this divergent getting larger duct, then our velocity is going to slow down, pressure go back up. And you could see that because in this funnel, what was happening, our little ping pong ball is here. As the air was coming down here, it narrowed right here, which did what to pressure? So pressure decreased, so lower pressure, and then as it widens, what is happening to pressure there? Increased pressure, and that holds the ping pong ball in place. Yes.
If it widens out, isn't that increased volume?
Volume
Increased pressure?
is technically staying the same because of our changes in velocity and pressure. Trying to keep our volume,
It's equalizing.
yes,
Okay.
equalizing out. So, if you have a funnel and a ping pong ball, you can do that trick with your friends. And tell them about Bernoulli's principle. And, yes, so start out with a set pressure and velocity. As it narrows, speeds up, velocity increases, pressure decreases. As we widen out, velocity decrease, pressure increase. We're just going over this briefly for now to introduce the concept if you aren't familiar with it. In a lot of other classes, well, tomorrow we talk about aerodynamics, and then especially in turbine class, turbines are built on the principle, on the concept of Bernoulli's principle, because all the air is going straight through. Well, sometimes it doesn't whoop-de-doo in the combustion section, but generally going straight through, and so we are narrowing, widening, so that we get the proper pressures we want in each area. So we're getting compressed, burning at the right pressure. Sometimes they'll have a converging duct, but the whole thing is converging, but the blades are diverging. It's really cool. Watch that turbine. The carburetor has a venturi in it to help to have low pressure to draw in fuel that's coming in at a higher pressure. You'll learn that in fuel systems. Tomorrow we'll talk about aerodynamics and how Bernoulli's principle can help describe lift, how air flows over a airfoil. So yeah, just introduction. So any questions on Bernoulli's principle? Now we're going to talk about sound. And it is defined source to make the sound, a medium, so it needs some material to flow through, whether air or water. In a vacuum, it can't travel. And a detector to detect the transmission. So, by this definition, if a tree falls in a forest and nobody is there to hear it, is there sound?
Yes.
By this definition, there's not. Depends what definition. There's still a source, there's still a medium, but there's no detector. So, now, we're just touching on this topic. You can go dive deep, have all kinds of debates on waves and all this stuff, but telling you what the FAA expects you to know for testing, not going deep into theory or anything. But you need to know that sound travels in waves, and I put, yeah, conceptually they're waves, with vibrating particles. So you could say we got sound, wave going with a wavelength. I'm going to talk about that. But technically, the particles are vibrating, but they vibrate in waves because they compress and then expand. The expansion is called rarefaction. You might see that word rarefaction later. So compress, rarefaction, compress. And that travels, if you look down from the top, you can think of sound traveling much like waves in water. Yeah.
That rarefaction is just literally the opposite of compression.
Yes.
So almost
Expanding.
expansion.
Yes.
Is it specific to sound waves or anything?
I've only seen it referred to with talking about sound, but don't hold me to that. So, the way they describe it is the progress of any wave involves two distinct motions. The wave itself moves forward with constant speed, and simultaneously all the particles of the medium that convey the wave vibrate harmonically. So, how many of you have ever used a tuning fork? Oh, good. I wish I had one. My dad has one. My brother has one. I never got one. But I have the next best thing. Wrench. And if I strike this, you can hear two different sounds, but that's because this is vibrating. I can't even feel it, but it's vibrating. And when I go like that, I just set up waveforms going throughout this whole room that hopefully all of your ears picked up. So we had a source. Our air is what the wave is traveling through, and all those particles are going boo till it gets to your ear, and so on. What other things you need to know about sound is it's determined by the density and elasticity of the medium. Good.
Yeah, I just looked up the word rarefaction, and it is a decrease in density or pressure within a medium.
There you go.
So often associated with sound waves
aluminum has more elasticity. The other thing with how sound travels is that if it's going from one medium to another, so like from air to water, it's going to really slow down and really lose speed, which is why they will make hearing protectors and earplugs out of foam, because foam is a very different medium than air, and that really slows down the sound and protects your ears. When we talk about sound, we have to talk about Mach numbers and the speed of sound. So a Mach number is the speed of an aircraft compared to the speed of sound. And the speed of sound at standard, we're going to talk about standard temperature at sea level is 760 miles per hour. So 760 miles per hour is Mach 1, and you may want to mark that in your book, page 5-48, kind of in the middle, right-hand side, 760 miles per hour. So if density and elasticity affect how fast sound travels, we're going to talk in a very short time about density. Why is temperature a factor in here?
Because the lower the temperature, the higher the density.
Excellent. And all you need to know right now is temperature very much affects the density of air. I'm going to talk all about that later today. So the terms you need to be familiar with: Mach 1 equals 760 miles per hour. Subsonic means less than the speed of sound, so we are all subsonic right now. Sonic means at the speed of sound. Transonic means at or near or passing through the speed of sound. And then what we all like, I think, is supersonic, above the speed of sound. So military jets, supersonic. Got some videos in a little bit. Frequency is another term. So if you're a music person, we talk about pitch, and that word pitch is often used to describe frequency, whether it's high pitch or low pitch. And it depends on how the frequency or how many waves you have per unit of measurement. So low frequency has very long waves, and then as we get higher frequency, the waves are happening faster and faster. And here's how they define it. The pitch of a tone is proportional to the number of compressions and rarefactions received per second. Easier to say longer or shorter waves. And which is in turn determined by the vibration frequency of the sounding source. So it's easy to see we got long waves going to short waves, but your thing that is producing sound, these are slower vibrations. This one is vibrating very, very fast, which is very important to know that sound is creating vibration. And I'll have a video on that later. Hold that in your hat. As we talked about, loudness. And loudness depends on the amplitude of the wave. So we got little seagull, he's going tweet, tweet. I don't think seagulls tweet, but anyway. A very shallow wave. But I'm not going to do it in a room anyway. You all have heard a very loud, squawking seagull screaming its guts out for somebody's french fries. What that looks like that, though. And you have very big waves. Just loud. So as it gets louder, the waves get bigger. talk about loudness, we have to talk about decibels. The intensity or loudness, I'm having too much fun, of sound is measured in decibels. And you can see a chart similar to this on page 5-33. Ah, too much fun, need some lemon. Alright. Of comparing decibels. So a decibel is a ratio of one sound compared to another. 1 decibel is the smallest change in sound intensity that the human ear can detect. Now I really wonder whose ear they use to make these measurements. 'Cause if it was my poor dad's ear, something would be very loud if I heard it. So, yeah, I'm sure they had this set standard. And this is a logarithmic scale. So, if you look in your chart, we got, 110 decibel noise, and then we got a turbojet engine. So the 110 would be twice as loud. So it gets bigger as it goes. It's not on here, but a rivet gun is about, on here, what do they have? Pneumatic drill is 80, but at 85 decibels generally, you need to raise your voice so others can hear you. And they recommend hearing protection. I've had to raise my voice to get all you to pay attention. So you've been putting off a good number of decibels. 90 decibels for 8 hours will damage your ears. So when we get into sheet metal class and you're out there, 30 people drilling and riveting, and a drill and a rivet gun are 90 to 95 decibels, gotta wear hearing protection. Or you will be like my poor dad who tells me, always protect your ears because I did it and now I can't hear. So, protect your ears. Okay. Yes.
It's been a long time since I did logarithms.
Oh.
So, according to the little graph here, the 90 decibels is half the loudness of 110. So is it every 20 it doubles?
Oh boy, I'd have to
That's what it looks like.
look up how to do logarithms as well. But yeah, it's like
It's
exponentially
exponential.
increase, not just
Not just linear.
correct.
Okay.
Like 100 is not just 10 more than 90. That's yeah. Here we go. So my sound worked. I hope it still works. Let me make sure. Yeah. All right. So here we go. And this is just so at 120 decibels, it says is the threshold of feeling. So, have any of you been to an air show where they're flying military jets, or they're doing the pyrotechnic stuff and setting off big booms, and you like feel it in your chest? That's a bullshit. If you haven't been to an air show, I recommend the one in Battle Creek, which will be next. It's always over July 4th. Fantastic. That one's cheap compared to a lot of other ones, and it's an excellent air show. But here's an example. You're not going to feel it unless I blow our speakers. So they'll do a thing, I won't tell you what part of the show it is, where they're doing this really cool formation with like 5 of them. Sorry, I think. And then one is off just out playing, and all of a sudden, yo, right off the deck, right over the crowd. Called it a sneak attack. So this is a video of that, and it's to demonstrate Doppler effect. Of course. Yes, of course.
The insurance company's goal is to pay you less. The only way they
supersonic flight. And have any of you ever heard a sonic boom? Yeah. So the really cool thing about the Battle Creek Air Show, they didn't do it this year, but they're slightly less restricted than like Oshkosh, which is super restricted. Everybody got to follow exact rules. There was one year, I think it was F-35. I forget which aircraft it was. We saw him coming like, oh yeah, we saw the whole cloud and everything. Bam! He hit the speed of sound. Like, you probably got in trouble for that, but it was super amazing. So this describes it. It has some good sonic booms, but then a good explanation of what's going on. Oh, there we go.
Recycling is more than sorting bottles. It's steel-toe boots, second shifts, machines roaring back to
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
So, back to when I talked about, so we can talk about sound as waves, and what is the other thing that's happening to all the air particles? Vibration. So, that's super important to think about when it comes to propellers and engines and lots of other part of our aircraft, because the wood, not so much, but aluminum has a certain vibration that the aluminum material will vibrate at certain RPMs, and the engine's got the crankshaft spinning and pistons moving, so that's got a vibration. So, it's really bad if both of those vibrations match up, and we get what we call resonance, and that can be very, very bad. We're going to talk more about it in propellers class and how we avoid that. If they know the resonance or the resonant frequency, there's a certain frequency that happens at and a certain RPM, there may be a red mark on your RPM gauge. You have to pass through that. You can't hang out in there, or your propeller won't be hanging on anymore. So, yes, if two pieces of matter have the same natural frequency, one of them starts to vibrate, it can transfer that energy wave into the other piece of matter, cause it to vibrate, and then it sets up resonance. And the anyone familiar with the Tacoma Narrows, Galloping Gertie? Excellent. I showed this video in this class, and then in cross class I show another video about it. But this one, people are just so excited about bridges. It's fascinating.
We're in Tacoma, Washington, and behind us is the Tacoma Narrows Strait Puget Sound.
There are twin suspension bridges that go across the strait. One was built in 1950 and the other in 2002.
Before these two bridges, there was another bridge over the sound, the Tacoma Narrows Bridge, or Galloping Gertie.
It was opened on July 1st, 1940. Because of windy conditions, the bridge started to move. Yep, you heard me right. The wind caused it to move vertically, up and down. That's when the construction workers gave it the name Galloping Gertie.
They tried several things to keep it from moving, but they didn't work, and in November 1940, just a little over 4 months after it was built, it collapsed.
A bridge collapsing like that might seem like a big deal. It was!
Fortunately, though, no one was injured.
The Tacoma Narrows Bridge became an example in engineering textbooks and spurred research into bridge design that is still influencing how bridges are built today.
The frequency of the wind coming down that channel that day matched the frequency of the material the bridge was built, and boom, busted the pieces. All right, it is time for a lab to be open. water temperature. Yay. If the aircraft is traveling at Mach 0.7, what's the aircraft's airspeed in miles per hour? And that conversion is just on page 5-32. That's 760 miles per hour. Take until 2:15. 2:15 to work on that lab, and make sure you grab a break in that time. basic foundational understanding. So starting on page 5-33, talking about atmospheric pressure and density, my hope is that you will understand density and not be thoroughly confused, because it is easy for people to get confused. So when we get to density, if you're confused, stop me and try to clear it up. So you might be thinking, as a mechanic, why do I have to know about the atmosphere? Pilots obviously are very concerned with the atmosphere. They want a good atmosphere, no big bad storms to fly through, checking the weather, know how weather works. But we need to know, because that affects engine performance. And also for troubleshooting, when your pilot comes back with complaints, you need to know what kind of environment he was flying in, and could this be causing carb ice? Or is it a really hot day? Is his engine not performing because of it's a hot day, not because there's something wrong with the weather? So those are some of the reasons why you do need a basic understanding of atmosphere. So I mentioned the other day a variation of this. We live at the bottom of a sea of air. And we have much pressure on us. If you take 1 square inch and take a column, the whole way up to the thermosphere, through troposphere, stratosphere, mesosphere, thermosphere, you don't have to memorize those. That will weigh, it will have 14.7 psi, which is why I said the other day, it's so hard to get out of bed in the morning because you have, so many pounds of air pushing you down. So, as we go up in altitude, pressure decreases because we have all these air molecules floating around, but those air molecules are getting further and fewer between as we go up, which is why if you go hiking out in the Rocky Mountains, a couple thousands of feet up in the air, it's a whole lot harder to breathe if you're wimpy like me than if you go for a hike in Michigan, because there's less air up there. And you can think of it, if it helps you, like Yertle the turtle. How many read Dr. Seuss Yertle the turtle? Oh my goodness, not very many people. Okay, short story. And those of you that read it, you can, if you have a better, shorter summary than I, you can tell your classmates at break time. But Yertle thought he was king of turtles, and forget if he wanted to see around the world also. Anyway, he made all his turtle friends stand on each other's backs so he could be king of the turtles. So if you think of yourself on the surface of the earth as the very bottom turtle, he had the most pressure because all these other air molecule turtles are stacked up on top of him. Yertle, no pressure. He's at the top. Guy at the bottom has the most pressure until Yertle had a bad day. He realized he actually was not king of the turtle. So, how this transfers is, I also mentioned this the other day, we can measure air pressure with a mercury barometer. So they took this tube, and it was 29.9 inches high, filled it with mercury, and that equaled out 14.7 psi. Now, how many of you pilots would like to fly around with a bowl of sloshing mercury? Me neither. No. So they came up with a much better instrument called an altimeter to show you pressure and your altitude according to that. And you're going to learn all about this in CASE's instrument class. But just basic knowledge for physics, it has an aneroid wafer which expands, contracts, because comparing the vacuum in here to a static pressure port out goes to a little needle that tells you how high you are above sea level according to the pressure of the day. So this is called a Coleman window, and that tells you the pressure. So standard pressure on a standard day is 290.92. The other day, it was maybe longer ago than I think, it was 29.92. Standard, but the pressure was, or the temperature wasn't standard. But
And we're at a higher altitude, it's not sea level.
exactly, right. But it was still 299. No, it's fine. So, like today, our pressure is, and this is just my Apple weather app. I didn't actually check the for real one, but it's at 30.24. So we would, this is a little knob. You set your pressure correctly for the pressure that you have, whether you call the local weather station for your airport. Put the correct pressure, it will show you on here your height above sea level, or your actual ground elevation. We'll talk a little more about that in a minute. But 1 inch square column of mercury, 29.92 inches tall, weighs 14.7 pounds. That's why 14.7 psi equals 29902. Mentioned that the other day. Atmospheric density and pressure. So I already said that pressure decreases with altitude. So as you go up, pressure decreases. So therefore, density, which you can think of air density as the compactness of the molecules. So here they're more compact, we've got a lot more molecules per cubic inch, less compact and more spread out. So do you think if pressure increases, what will happen, or no, let's stick with it. So pressure decreases, what will happen to density? Will it decrease as well, or will it increase? We've got some of this, we've got some of this. Correct. So as pressure decreases, density will decrease. You can see it here. Here we have 30.92 inches of mercury pressure, and then we decrease the pressure to just 29902, and density decreases. That's a place to go. And less pressure, less density. Temperature has a very big effect on density, and somebody mentioned this earlier. So if temperature drops, like it's going to, in a short amount of time, temperature drops and it gets colder, what do you think happens to the density or the compactness of the air molecules? Ooh, we have, you're right. Density increases, because as it gets colder, so when you think of a gas, what's happening if we heat up a gas? What is, the molecules are going, yeehaw! But when we make it colder, the molecules are like, ooh, it's cold, and they get closer together and vibrate a little less. So our density is going to increase. So if turtles help you think about pressure, as you find a stack of turtles, pressure gets less. Cows can help you think of temperature with effect on density. If you ever observe cows, and I've actually have observed this, when it's winter and cold, the cows generally, of course, cows that don't adhere to the Christina rule, cows generally are all bunched up and trying to keep each other warm, and they're dense and compact. But on a nice hot summer day, now they might be all under a tree, here is a graph of our layers of atmosphere. Again, you don't have to memorize this, but the troposphere or troposphere, however you choose to say it, is where flight happens, is where weather happens, up to not quite 10 miles up. And then, so temperature decreases, and then we have this weird thing, it kind of increases in the stratosphere, but then gets colder and colder in the mesosphere, and then does some wacky stuff in the thermosphere. But generally speaking, temperature decreases with altitude. So it gets colder and colder and colder. So what should happen with density as we get colder and colder and colder? So density, if we get colder and colder, it should get more and more and more dense. Pressure, as we go up, there's less pressure, so it should get less dense. So, what does happen to density as we go up in altitude? Do the pressure turtles win? Do we get less dense? Yeah, less dense? Or do the temperature cows win? Do we get more dense? How many say pressure wins, we get less dense as we go up? How many say, oh, cows win, because it gets colder, we get more dense as we go up? And then a bunch didn't vote. So yeah, pressure drops more rapidly with increased altitude than temperature does. So the net result is that density does decrease with an increase in altitude. And turtles win the day, cows can go bye-bye. So this is a nice graph down at sea level, lots of molecules, nicely close together, very dense. As we go up, they get more and more spread out, less and less dense with altitude.
So is inches of mercury a measure of density or pressure?
Pressure. And you may want to mark this in your book on page 5-37. Let's skip over a little bit to get the numbers for standard atmosphere. So when we're doing performance checks on our engines, there's lots of numbers we have to get, like power settings and mixture settings and all kinds of stuff. But it's going to depend on your pressure and temperature, and we'll talk about that a little bit later. That does affect your engine performance. So since every single day is different from the day before it, we need some standard to compare our results to. So the United States, and thankfully the United States in this one lines up with the International Civil Aviation Organization. So they all agree. And standard pressure at sea level at the 40th parallel north, probably because that's where they were when they did these tests, which is a little bit south of us. Looks like it almost runs through Pennsylvania. Pressure, standard pressure is 299 or 2 inches of mercury. Standard temperature is 15 degrees Celsius or 59 degrees Fahrenheit. And acceleration due to gravity is 32.147 foot-pounds per second per second. So make sure you mark that in your book, and that's a good thing to memorize as well. Now, lots of things happen, like hurricanes for poor Florida, that drastically change that and make it very unstandard. Yeah.
Is there a calculation you have to do for, say, if you're at the equator instead of 40 degrees north?
I have not seen where you have to figure
'Cause I
difference in
I
latitude.
didn't even know it was at 40 degrees.
Right, that's just
I
kinda
thought it was
like-
just like sea level, sea level.
Right. No, the biggest factors are altitude, pressure, and temperature is generally what you're factoring. So now, I hope you don't get confused on the next part. This can be a little tricky, so try to stay with me and ask for clarification. So there are types of altitude you need to know. Pilots hopefully know this forward and backward, but you'll be quizzed on some of these. So first one, simplest one I think, is indicated altitude. That simply, now you can go way deeper with all of these in pilot stuff, but keeping it simple, keeping it very basic. Indicated is simply what you read off of the altimeter instrument. We'll talk about reading altimeters. So you can think of it as what your instrument indicates. That's it. So indicated, think instrument. What do I read on that face? Could it be wrong? It sure could. Oh no. But indicated for your instrument, yeah.
What page is this?
This is, this is just some building blocks for later. It might not be in this book, but you'll find prepware questions on it, which is unfortunate, but that's why we teach it in class.
Oh,
Yeah, thank you for asking that.
yes.
Cause yeah, and hopefully people can bear me to paying attention. So yeah, indicated what you read off the altimeter. Pressure altitude, so remember standard pressure is 299 or 2. So pressure altitude is if you take this little knob and you turn it so that 299 or 2 is at the pointer in this little window. It will be the altitude your altimeter reads if you have a properly functioning altimeter. Altimeter set to 299 or 2, standard pressure measured above a standard reference point. And here we have pressure altitude going to a standard datum plane, a standard that they set up. We're not going to go deeper than that. Just know that there's a lot more that we could dive into, but we don't have the time or the need for it in this class. Then, and that's just, yeah, pressure altitude set 299 or 2 in your Colesman window. Read what your altimeter said. That's what you need to know for this class. Very important for aircraft performance and doing maintenance checks is density altitude. And that is taking your pressure altitude, so however, whatever your altitude is, corrected for non-standard temperature. So anytime you are not at 59 degrees Fahrenheit, you have to adjust because your airplane, due to density changes because of temperature, your airplane is going to feel like it's at a different altitude. So if I'm in Florida at sea level and my pressure is 299 or 2, but it's a wonderful 100-degree day, what happens to the density as compared to a 59-degree day? Less dense. So my airplane is going to feel like it's at, will it feel like it's at a higher or lower altitude? It'll feel like it's at a higher altitude because it has less dense air to take in to combust in the cylinders, less air to produce lift, so it's going to take me longer to try to take off. My engine performance might not be great. So density altitude is very important to understand. And then something that some of these are compared to is just true altitude, and you can see that here. So another term to be familiar with is mean sea level or average sea level. So true altitude is truly where are you at above sea level? So that is truly the true truth. Altitude above sea level. You may hear the term absolute altitude or altitude above ground level, and that's just whatever terrain you're flying over, the distance between that terrain and you. You won't really need to know that too much other than if you're flying along and you're not paying attention to absolute altitude and you go too low, you absolutely will hit the terrain. So we're going to talk about altimeters and then more about density altitude. So here's a nice, if you're not familiar with altimeters, a nice cheat sheet that you can take a picture of or you can look it up on your own. So it's kind of like a clock. We have our 100-foot pointer. So as this starts to turn, we're climbing through 100 feet, 200, 300, 400, 500, 600. And then when we get to 1,000 feet, our 1,000-foot marker will start to turn. So when this short guy is here, we're at 1,000 feet. And if we keep climbing, eventually this 10,000-foot pointer will budge, and then it could be 10,000 feet from good flying aircraft. So, if this is my 1,000-foot pointer, and this is my 100-foot pointer, what is that altimeter reading? Yeah.
5,800?
5,000, because we read this one in thousands of feet. He's already budged, so 5,000, and then 800. Bonus question. If this pointer was right at this first tick mark, what would that be? Anyone?
5,820.
That would be 5,820, because each of these tick marks represents 20 feet. And when you become a smack commercial pilot, you're going to nail in between those. Yeah, I didn't. What is this one reading? Any volunteer? Or I can.
2,500.
So 2,500. And what is this one reading? 7,400. Excellent. So, yes.
Is there ever like a tens of foot needle?
Yes, that's this one, 10,000. Is that what you...
No, like instead of the smaller 10.
Oh, so
you've got
this
like
is our
10 or
100-foot.
1,000.
This one is our 100-foot needle. So here are 400. That first tick mark for 20,
Yeah.
for 30, and then halfway, of course, would be 10. So you just have to look at it. Get your eyeballs trained.
I have glasses.
So this is in the, one second, I'm going to show you what this looks like in real life. Switching over to there. And I have, now this is Case's altimeter. It has his name on it, so I need to be very gentle. It's a precious instrument. So, on here, yes, good. You are going to be doing a lab in which you need to find pressure altitude of today or tomorrow. So, pardon me a minute. What should I do to this altimeter so that it at is actually standard. Very, very rare. And density altitude very rarely will be true altitude. So this is a snapshot from, I think, 2023. And you can see, now this is in millibars, which is the metric measurement of pressure. And 1013.25 millibars is equivalent to 2992 inches of mercury. So 1013, this one's close, but we got low pressure systems, high pressure systems all over. This is at surface level. On top of that, we have temperatures way above standard. This was a wonderful day. It's a little cool in Michigan, 65. Oof, but very warm, nice warm summer day. So pressure, weather systems changes, temperature changes, density. So here's the thing I want you to hopefully wrap your mind around and not get confused, is the term density altitude when you're going to have high density altitude and low density altitude. The term high or low is going to refer to altitude, not more or less dense. So 5,000 foot would be a higher density altitude than 3,000 foot would be a lower density altitude. It's talking about altitude, not that it's more or less dense. So just density altitudes effect on aircraft performance. Some of these are a little edited wrong, but have a cool morning. Pressure altitude, all of our pressure altitudes are 6,500 feet above mean sea level. Starting out, temperature 50 degrees Fahrenheit. Density altitude, now this is a little odd calculation, but 7,418, and it takes us 3,110 feet to clear a 50-foot obstacle. Now we raise that temp to 68. Boy, we've got 8,539 above mean sea level density altitude. So our airplane feels like, because it's warmer, it feels like it's at a higher elevation, even though we're still at 6,500 feet. Now it takes us 3,375 feet to clear 50-foot obstacle. And then, oh boy, that's a beautiful afternoon, 104 degrees Fahrenheit. And now our density altitude went from 7,400 to 10,135 feet. And now it's going to take a very long time, almost 4,000 feet, to clear a 50-foot obstacle. So, very important to be aware of as a pilot, but be aware as a mechanic, because if your pilot comes back and says, I took off almost a whole runway, my engine, you did something wrong to my engine. You can be like, well, buddy, 100 degrees out there, did you calculate density altitude? Another, so, yes, density altitude matters. That's my next slide. Just showing you nice and cool, compact, lots of molecules, heated up, or spread out. And here, density altitude matters. It can mean a difference between actually taking off while you're still on the pavement or running off the end and having a very bad day. So, a low density altitude, remember, low altitude. Airplane thinks it's a low altitude. Is this more, I don't want to get you confused. Okay, so low density altitude means we're at low altitude. High density altitude means the airplane feels like it's at a high altitude. which one of these is the air more dense? Yep. Low density altitude is actual denser air, more compact molecules. Yes.
I understand the temperature correlations, but how does humidity affect aircraft performance?
We're going to talk about that now. Very good question.
So excited.
I know. It is. So remember that more density, greater density equals better performance. We got more molecules giving us lift, more molecules for our prop to grab to produce thrust, more molecules to burn in our engine to give power. Here's a chart that has to do with density altitude. And for pilots, you may have had to deal with this side. We're going to take that we're at 292, so no conversion factors. We don't have to worry about this in maintenance. Woohoo! But the way you use this chart is if I have a pressure altitude, which how did I find pressure altitude? Oh. Yes. Set 299.2 in my Colesman window, and we got 4,000 feet. Woo! So that's this line here. And I'm at 60 degrees Fahrenheit. So we got, be careful when you use this because we got Fahrenheit on the bottom, Celsius on the top. So we're going to find 60 degrees here, and that's this blue line there. Come up till we meet our 4,000, and then you come straight across. We're a little bit below 5,000, so these are in increments of thousands. So about where, did I do that right? Yeah, pressure altitude of 4,000, and, oh yeah. About what density altitude does that look like?
4,800.
Yeah. I'd say that's close to 4,800, yep. If, so actually I'll leave that there. So if we're still have a 4,000 pressure altitude, but now it's my kind of day and it's 100 degrees, we come over here and we follow this blue line up until we hit 4,000, and right about in the middle, across, and there's 7,000, 7,500, so like 7,200-ish. So you can see in one day, well, yeah, it could go from 60 to 100. We went from a little under 5,000 feet to a little over 7,000 feet density altitude. So that can have huge impact on your aircraft.
So I'm a little confused, I think. So you're still flying at 4,000 feet?
Yes.
But the way that everything operates is it's like operating at like 7,000?
Exactly.
Oh.
Yep. Yep, that's exactly right. Yes. And especially for takeoff and landing, pilots have to do performance numbers based on density altitude because the higher density altitude, the longer it'll take to take off, and your landing roll will be longer, and your engine performance won't be at peak. water content in our atmosphere. And water in our atmosphere can be in the form of droplets held in suspension, which we see as fog or clouds. Or it can be as a result of evaporation and water vapor, which is humidity. Now, here's something you'll need to know. Humid air is less dense than dry air because in a volume of air, we're measuring how many air molecules are in there. And if our water vapor is kicking out our air molecules, we have less air molecules, so it is less dense. But dry air, no water, you have a volume of air, all air molecules, more dense, more air molecules. And here you go, higher the temperature, the more water vapor the air is capable of holding, assuming you have a constant pressure. Why do you think that might be?
The air molecules are expanding.
Yes, there's more space for the water vapor. So as you heat air up, molecules are going, yeah, and they're more separated from each other, so water vapor can see, ha ha ha, I have a nice little home, and fill up those empty spaces. Two terms to be familiar with is absolute humidity, and that is the actual amount of water that is in the air. What we hear from weather reports and different things is relative humidity, and we go again, a ratio. Relative humidity is a ratio of the actual amount of water in a volume of air compared to the maximum amount that it could hold. So we have a certain amount of water vapor at 30 degrees Celsius, 28% relative humidity. We could have a lot more water vapor in that volume of air. But as we cool that air down, those molecules are getting closer together. So in a volume of air, now our same volume of water is taking up more space because we're getting denser with our air molecules. And we get denser and denser, it suddenly condenses. So when we have 100% relative humidity, that volume of air is said to be completely saturated and has all the water vapor it can possibly hold. Then we have the term dew point, which is the temperature to which humid air must be cooled at a constant pressure until it becomes saturated and it'll condense on surfaces or condensation occurs. So here's a little fun physics problem for you. This was not in my apartment now, but where I lived before that. I stepped out of the shower, so I had lots of humid air going on, and I noticed condensation here, but not here. What do you think was going on? Yes. So I was like, that's weird. It's coming over here next to this light bulb, but nothing here. So I had just changed this one, and I think it was LED, and this was an old, hotter light bulb. So this was warming up the glass because the glass was cooler than the air in the room. So any water vapor against the glass condensed onto the glass, but this was warm enough that it didn't reach the condensation point.
So dew point takes into account relative humidity?
Yes. Yep. it's less dense, so I already talked about problems with that. But now, not only is it less dense, it contains water. Water doesn't burn very well. So your engine is like, any questions on any of the things we have covered? All right, I'll open up your last lab for today. And don't get too excited. There will only be one more after that. So I'll take it. And I want to go over a couple things on this lab with you. Alright, first of all, it says make sure whenever you do these labs, you're reading the instruction little bubble. Complete the following questions. You'll need to use your textbook and the Jefferson Private Pilot textbook, and that's found in the digital publication library. So is everybody familiar with going into the Google Drive, our maintenance manuals and reference textbook references? If you're not, you can grab me or a friend and we'll show you how to get to that. So the different altitudes that is unfortunately not in your textbook, you'll find that stuff in a private pilot textbook. Point out number 6. Watch the animation below. The mercury in the glass tube of the mercury barometer has risen to 744 millimeters. What is the atmospheric pressure? And your options are several different options, but what will be helpful to you is your handbook, converting millimeters to inches, page 8. So on page 8 you have inches, 25.4, yet millimeters, so that's a handy little tidbit for you. Number 22 is a problem you'll need to set up as a ratio. So it says at 70 degrees Fahrenheit, a cubic foot of air will be 100% saturated when it holds 7.9 times 10 to the negative 4 pounds of water. If the relative humidity is 55% under the same conditions at 70 degrees Fahrenheit, how much water is in the air? How would you set this up? I think I hear you're thinking, right?
Multiply the pounds of water by 0.55 or 55%.
So let's do it this way. I need it to become a proportion. So I'll have something equals something. So I'll start you out with, we're comparing 55% and 100%. So that'll go on one side. So we got 55 compared to 100. So which of those numbers equals my 100%?
7.9 or 8, 9 times 10 to the negative 4.
Yes. So 7.89 times 10 to the negative 4 is how much water it holds at 100%. But we want to know how much it holds at 55%. So then you just solve this like any proportion problem. So if you want to copy that down, you can do So, if that gets confusing, just grab me. I can talk you through that. Then, question 28 is a fun one. It says, for this portion of the lab, the instructor will assign students to an aircraft with a functioning altimeter. Using the altimeter, determine pressure altitude. How will you do that? Somebody hasn't answered yet. Uh-oh. Okay, somebody has answered. How will you find pressure altitude with a altimeter? Yep, put 299 or 2 into the Coulson window. And then, to figure out the actual temperature, call our AWAS at 616-523-1852. Hopefully it's working. It's just a recorded voice that you'll hear. If it's not working, you can use the whatever weather app for the temperature. And then, using the pressure altitude that you figure out from the altimeter and the recorded temperature, take this density altitude chart. Here's your pressure altitude. You'll come down here to the bottom, go up till you take your pressure altitude from your temperature and go to left. And these are in thousands. Questions on that? Alright, if everyone can pay attention, I will list the aircraft that have relatively functioning altimeters. So the best one, at least this morning, was the 182. It was pretty accurate. So I would recommend using the 182. If everybody's around that one, you can use the 210. Now that's a couple of 100 feet off. But, it is in this question. You need to record the make and model of the aircraft you're using, so make sure you do that. Then I'll know, oh, okay, and then just don't try to compensate, just write down exactly what you read, and I'll know, oh, they used a 210, so this is a reasonable density altitude, pressure altitude you came up with. So make sure you record your aircraft. The Apache, so I got in there, it was super messed up, but I straightened it out and it seemed to be functioning. So you can use the Apache. You can use a Cherokee, that one's about 100 feet off, but that's manageable. So 182, 210, Apache, or Cherokee. Alright, the rest of the time is lab time.
Is that AH-64 or 235?
For what?
The Apache. Is that 235?
235, I think.
Was it done?
No.
The Apache helicopter.
Oh, it's a helicopter. No, so Piper Apache and then Piper.
That's the twin out there.
Yes.
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 Besides
Yeah,
the
because they have the
King.
Apache and then Cherokee is 23 one.
I mean, beach jet, 414 Prince, and then the other one would be the 35 Apache.
Yes.
Okay.
It's in there.
You put the twin Apache cold on the
Composition of the atmosphere.
That's the standard.
Wait, when was the way you speak?